Okay, I was told by Ingo that I was here to liven everyone up, but you all seem very excited still, so it's good to see. It's been some good talks today. So my project, or my talk, is about making music, but making it in a very simple way. I've experimented with music before in Clojure, and there's some really good libraries out there. Overtone is great for like timing, making synthesizers, playing samples, all that sort of stuff. And Elder is really great for composing musical scores and manipulating those. And those libraries are great. And in true Clojure style, if you look up great, it also means big. Very big things. They're very difficult to understand. And I don't want like big complicated things. I want like the bongo drum of Clojure music programming. It has to be like super simple. One of the things about Overtone and Elder is they represent the end of the journey of two great Clojure programmers, of their explorations of music. And it's very difficult to pick up where they left. Like it has like their flavor. And I want to start my own journey. And this talk is sort of a DIY guide for you to make stuff yourself. As you can see, all the slides also made by hand. So it's all about like removing all distractions, writing stuff down on paper, for example, as someone has alluded to earlier today. So this is all about stripping away stuff, stripping away dependencies, understanding the basis of music, electronic music programming in general. There's like an ethos or a quote from punk rock which goes like, here's 3 chords, now start a rock band. This is basically, here's the minimal set of music theory and technology you need to understand to go out and start a band or, a solo bit of music. And it's going to be at different cost scales, and we're going to start with it costing nothing, and it's actually going to cost nothing for most of the time here, if you have a computer. So the basic setup of our system is this. This is like an abstract representation of a system. We have some sort of keyboard or sequencer, which is what determines which musical notes we want to play. So if you play keyboard, you know that each key represents a musical note. That is basically data. It's data from the keyboard into something that generates sound, which could be like a synthesizer, which might be like a physical piece of hardware, like what I have lying here, you can't see. Or it could be a virtual synthesizer running inside of your laptop. And the MIDI protocol is battle-tested, so to speak. It's from, the protocol was defined in 1983, and it's, in its simplest form, super simple. So basically, you have one type of messages that correspond to pressing down like a note on a keyboard or sending a note from a sequencer of sequenced notes. That's just a number, encoded in some, as a package. And then you have another type of package, which is you releasing the note again. So you move your finger away from the piano or the keyboard. These are the only 2 pieces of data of the protocol that you need to understand to get going. And I'm going to prove that to you by doing the most scary thing you can do in a tech demonstration, which is to do a live demo. So in here, don't know if you can actually see this. Better? Yeah. Cool, all right. So as you can see here, the project file of this thing has no dependencies. We're just running on like the bare JVM. We're going to be using the MIDI system that comes built in on your JVM. You don't need to do anything that's already there. We're just going to use 2 classes, the MIDI system itself and these MIDI messages. If you execute MIDI system, get MIDI device info, you can see all the devices that are running on your machine. And there's a fair chance there's already a couple of them running without you even knowing. In particular, the Jurville one is built into the JVM. That will always be there. That's the one we're going to play with first. I've written like a small helper function for just getting out any given named MIDI device. And we're now going to open the Jurville MIDI device. We're going to grab a receiver, and we're going to send a note on to play a note. It's a C. And then a note off after 2 seconds to actually stop playing that note. Oh, brilliant, the sound works. Cool. Thanks, sound guy. Thank you very much. Whew. All right, that's a scary bit taken care of. And of course, we can also play like a sequence of notes. You all know Clojure sequences, I hope. So here's a small helper function that takes a MIDI device or a MIDI receiver, and then so like there's a virtual MIDI device. You saw the MIDI cable on the drawing before. There's like a virtual MIDI device inside your JVM. It's sending MIDI protocol messages from one running process to another in there. So we're going to open such a MIDI device, get a hold of a receiver, which is like a synthesizer. That's this piano you just heard. That's the synthesizer bit of our drawing. And then it's going to play us a small scale. There we go. So pretty easy. We only know about like 2 very simple messages about MIDI devices, about MIDI receivers, and numbers. We know what numbers are. And we've now started composing music. It's pretty cool. And we're working with Clojure sequences. So hopefully you also know there's lots of functions for manipulating sequences in Clojure. It's one of the selling points, right? So let's try and compose a small melody. Let's just play 30 notes of like this small piece I come up with here. The same piece reversed, I think, almost the same piece reversed, and then shuffling something around. The idea is here to just play around with what you already know of integer manipulation and try playing it and see what it sounds like. There you go, abrupt end there. So the idea here is, it's the punk rock band idea, right? We know 3 chords, we know the Clojure ecosystem. We now know how to send MIDI devices. So we're making punk music, basically. Music is often like very repetitive, like these loops, you play a melody, then you repeat the melody, especially like modern dance music, that sort of techno, that sort of stuff. So since that's a pretty easy genre to emulate, we're gonna do that. And we're gonna use simple Clojure data structures, off-the-shelf stuff. So we're going to define an atom for holding our melody. And then we're going to have a helper function that takes an atom as a future to start this in a different thread so we can still interact with the REPL, right? It starts up a thing that just loops over whatever's in the atom, plays it, and when we put nothing in the atom, it terminates, so it doesn't idle and kill our laptop. So let's say I want this simple melody. I can just reset the atom, and then start my player, and it will sound like this. All right, so it's pretty easy to get going and see how you can compose stuff without any fancy libraries, just concatenation of sequences. And having this running in the background removes all delay. Swapping an atom is really quick, and it's definitely very bunker drum-like. I feel like. I have been cheating a tiny bit. If you notice, I haven't just done like the note 60, note 61, 62, 63, and 64. And the reason why I haven't done that is because that often doesn't sound very nice, basically. So this is where the talk switches into a bit of music theory. So there's certain notes that sound nice together, and there's like patterns for which notes sound nice together. So if we try something completely random like this, hopefully this won't sound amazing, although there is a chance that this is a hit. So these notes are like, all right, but it's not really, doesn't sound great. And that's because they're not part of like the same scale of tones. So we've looked at like the minimal punk rock theory of MIDI notes. Now we're going to look at the minimal punk rock music theory that you can get away with. I am not a trained musician, and I'm not an electrical engineer either, but I built this thing, as we're going to look at later. So this is truly ghetto or punk rocky, I say. So the idea is there are certain patterns that you can use for deriving which notes sound nice together. And basically what you do is you pick a root note. So in the first drawing, I picked C, which is the leftmost note on there, marked with a dot. And then you jump past keys according to a pattern to pick out the notes that make up, for example, C major. So the major scale defines like the length of these jumps. So you start in C, then you jump twice to the black key, to the white key. Then you jump twice again, black key, white key. All right, now I got the 3 first ones. Then you jump only once, and then twice, 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 and you're back to start for one more jump. All right, and then if you shift and you start in D instead of C, and you do the same exercise, you'll arrive at the D major key that I've drawn up there underneath. Major is not the only key. There's also like minor keys, and there's all sorts of different modes. But common are that they all sound nice. That's what we're looking for. So this looks like algorithm. Algorithms are like fun to implement in Clojure. So here's a small helper function that takes an offset, that's like the root node, and a tonal pattern on the form tone or semitone, where tone is jumping twice and a semitone is jumping once. It's just to have some lingo there. We could have just used the numbers. And with this function in hand, we can generate MIDI notes given the first offset, which is just a number, and a pattern. So let's try and take the major scale starting at MIDI note 0, get out some of the middle notes and listen to it. So this is our melody. Let's try and start it. Sounds great, right? Or, you know, sounds not awful. And then you can take, this is where you can really start having fun, to have fun with your favorite sequence functions. So let's try picking the Locrian mode, starting a bit further up, pick out some notes, repeat them, cycle, sample them, and take 10. Right. Whenever there's a nil, that corresponds to a gap, by the way. So what does it look like? Looks like this. Oh, it looks interesting, doesn't it? So a bit of repetition here. Let's try and listen to it. It's a bit like a nursery rhyme type song. We're getting there. It's not quite punk rock yet, but we're getting there. There's also often repeating patterns. There was actually by accident a bit of a repeating pattern in what we just listened to. But we can create that repeating pattern by hand. So let's say that we want two patterns, an A pattern, which is 4 bars long, and a B pattern, which is 8. We can extract those from the same sequence of numbers to make sure they're in key. And then we can yank them together. So here you can see there's a pattern with 5170, some spacing, 5170, and then there's like a different melody after that. So let's try and listen to that. So now we're starting to like think about what kind of patterns we want to generate using simple Clojure functions. Cool. All right. So far we've been playing around with the internal keyboard that's in your JVM, and you can play around with that today. But everything you'll make will sound like it's nursery rhymes or classical music or so stuff. It's not very modern maybe. And we can get other sounds inside the JVM, like the built-in synthesizer has that possibility. The problem is that we need to go out and find the big book of Java. And we have to do quite a lot of work, and it's not very bongo drummy. You can really see that Java has roots in the enterprise software industry, which is fine, but it's no longer a fun afternoon project doing this sort of stuff. It becomes like a big enterprise piece of code. So what can we do instead? Well, we're already talking about this MIDI signal that's going on inside the JVM, and there's nothing stopping us from sending it outside of the JVM and hooking it up to something else. It can be outside, like a physical piece of hardware, or it could be a different software synth. So before we had the JVM and the synthesizer living inside, the keyboard and synthesizer living inside the JVM, let's try and break out the synthesizer, but let's just keep it inside the computer. And then let's, instead of the JVM process MIDI signal transmitter, we're going to use a small driver that runs inside a laptop. It comes with all Mac laptops. There's something similar for Linux. And then use that for sending signals between processors running on the same piece of hardware. This means that the JVM keeps doing what it's good at. The JVM is good at letting us manipulate these sequences of numbers and sending them off. And it means that all the heavy lifting, the stuff that needs to be closer to the iron, basically, can run in a different process, maybe written in C and something similar. Right? If you look at overtone, it also offloads all the heavy lifting to a C implemented system. So I'm going to show you one now called Helm, and to keep it cheap, it's cost nothing unless you donate. So Helm is a software synthesizer. Oops. I wish I could find my mouse. There it is. It sounds like this. Okay. Can sound like this. and you can pick other sounds very easily. So let's try this one. Oh, it sounds amazing. So you can see like, it's very quick to try out like some different sounds. It has all sorts of settings as well you can play around with to get intuition for how synthesizers are formed in a completely different way than loading pre-made synthesizers inside the JVM. And how do we connect to it? Well, it's as easy as we did before. There's a different MIDI device on my laptop called the Busone. I've hooked that up to this to the Helm synthesizer. So if we redefine the player to use Busone instead of what we were using before, and we just repeat our exercise from before, start the player. Okay, it's beginning to sound a bit more electronic music. Let's try and switch this one out. There we go. So it's always about choosing the path of least friction. The least amount of friction you can do to get interesting synths or stuff into your coding environment is to have them running in a different process and just hooking them up with MIDI. MIDI, as I said, like it's a punk rock thing of equivalent of like 3 chords. It's very easy to understand and wrap your head around, but it opens up like tons of possibilities, and that's what you want, right? You want to be able to connect like a wide variety of stuff, and the MIDI protocol allows you to do that. So far, we've had like repeating patterns, and it sounded all right. At this point in time, I began to get creative, and that's the point of this journey, right? You start out understanding like some fundamentals, and once you pick those up, you're free to use existing knowledge or try to be as creative as you can and try out like other approaches. I have a background in bioinformatics, and one of the things that we always asked to do is to compare DNA strings. So I thought, wouldn't it be fun to try and compare musical scores instead and see if we come up with like some fun algorithm or some way of composing music using that. So in bioinformatics, if you compare 2 DNA sequences, you can measure the distance between those as the amount of edit operations you need to do to get from one to the other. So in this example, you could delete the C, you could delete the G is called the substitution when it happens in the other string, and you can replace the C, no sorry, it's an insertion when it happens in the other string, and you can substitute the C for an A. So there's 3 operations that will take you from the top string to the bottom string. That means the edit distance is 3. You can calculate the edit distance using dynamic programming. In this beautiful diagram, I demonstrated the matrix that you could fill out. If you're interested in the details, you can either look at the source code or you can look at Wikipedia. It's pretty well-known algorithm. And this dynamic programming matrix defines a path from one string to the other string. And if you traverse that graph, right, that path all the way back, and execute the operations one by one, you get what's called like the trace between the two. So it's intermediate strings. And if instead of, so there's cat and hats, like you substitute C with an H and then you add an S, for example. If you have 2 melodies instead of 2 strings, one way of having like a smooth progression from one to the other is to look at the trace, look at the elements in the trace, and picking them at random and concatenating them. Right? Then you have like a form of progression. Right? This is very experimental, of course. Right? So let's try that. If we have an edit distance trace function, and we ask for the trace from cats to hats, we get cats, hats, hat. Right? But now we're going to do it with MIDI notes instead. So let's say we pick our favorite MIDI notes here again. We generate a sequence called A at random. We generate a sequence called D at random. We find the trace. We find 2 intermediate sequences called B and C, and then we concatenate it all together, and it looks like this. So we need to get from 56 to 58. Oh, this is a boring one. Let's get another one. That's a bit more interesting, I think. Even more interesting, please. This is coming up. This is a problem with randomness. Not random enough. This looks pretty random. Cool, all right, let's listen to this one. Right, so you see there's some progression, right? And the point here is like try out some wild ideas, and everything's just number sequences. It's super easy to manipulate. It's super easy to do. The problem is that all our music now has been like very static. There's been no like consistent rhythm in it. We've just been looking at musical theory from the point of like what's notes. That's fun up to a degree, but I started being more interested in like how do you get interesting rhythms. And there's you can get some interesting modules you can hook up to your music equipment at home. For example, there's a qubit pulsar which costs like 250 euros, which implements something called Euclidean rhythms. And Euclidean rhythms, the theory is you have a number of beats, for example 16 beats, and you select a number of pulses, and then the algorithm basically evenly distributes the pulses over the number of beats. And if you read articles about this, there's some interesting analysis of world music that shows that different values of N and L, like beats and pulses, correspond to different types of music in different cultures. It's really interesting, and you can implement this in Clojure for the cost of nothing, right? So I thought let's try and do that and play around with it and see if that like yields some music that we are more interested in hearing. So here's an implementation of Euclidean Patterns. If you say we have 16 beats, we want 4 pulses, it'll even distribute out this pulse. It's called foo. We can use numbers instead. Then we're back in the MIDI game, right? Let's try and have a bit of maybe a bit of boring rhythm here. So this is all right, but the problem is we're only playing one note over and over again, and that gets a bit boring. There's not much of a melody in that. So we need to bring back our theory from before where we were playing tonal music, where the notes were in the same key. So here's a very simple function. It could probably be refactored to read a lot nicer, but this means that everything's in one slide, and that's good. So basically, we're now going to play multiple tones at once instead of just one tone. And then we're going to run the Euclidean rhythm algorithm for different notes and then layer them on top of each other. So we're going to play multiple notes at once, possibly at once, and then listen to what that sounds like. So we're going to define a polyphonic player, which does this. So let's try and create a melody. So here's two very simple patterns. I'm shifting one of the patterns so it gets a bit more interesting. I also need to start the player. Okay. So you can see like how you can start layering these things and have more fun out of it. You can also remove the tonal aspect of Euclidean rhythm usage and hook it up to a drum machine instead. So as an example, here's a drum machine that also hooks up to the MIDI bus on like a local computer. I've lost my mouse. Anyways, we're going to listen to it in a bit. So you can play it like straight by just pressing the buttons here, or you can play it by setting some drum notes. Here's the MIDI drum notes for this particular drum machine. If we open that up and we open up a virtual bus, it's hooked up to this drum machine. Let's listen to the drums. There you go. We just went through the sequence of MIDI notes, played each of them. Pretty standard stuff. So let's redefine our polyphonic player to open up the bus that contains the drum machine, and let's try and create some funky rhythms. Cool. Okay, so that was the implementation. At this point in time, as you can tell, I'm manipulating by running around the repo, changing some numbers. It's not very hands-on, it's like a lot of typing. And around this time I discovered that there's lots of people out there building their own physical hardware for doing music and hooking up in all sorts of weird ways and having lots of fun. And I got insanely jealous, especially of Sam Battle from Look Mom No Computer, who's built a Furby organ, so you can play this thing as an organ. Highly recommend checking it out. It's very fun. It's very funny. So I set out to build what in my vision would be a beautiful piece of engineering, an Arduino sequencer, which operated on the basics of Euclidean rhythms, hooking up to like a live drum machine, which I'm just going to feed through now so we can actually listen to it. Right. You need a bit of hacking to get this to work, unfortunately. There it is. So there's a physical piece of hardware here that those close by can see. It looks like this. Beautiful. It goes into production for Christmas sales. Maybe not. And it sends MIDI signal through this cable to a drum machine as here. You can hear. Hopefully a bit of a drum there. And then, it sends music out, sends sound out to the real world. And if I turn this thing on, hopefully it will turn on. Poof, there you go. See, it comes pre-configured with like a very simple rhythm. And then now I'm going to manipulate the 8 tracks of sounds on this sampler, and it's going to use Euclidean rhythms to play music. And I don't have like a piece of music thought up. I'm just going to do this live, and hopefully it'll sound all right. Let's try and listen to it. So as you can hear, it's way more hands-on. It's much easier to manipulate rapidly. You just twist the knobs until you get the correct settings. It's really great fun. And building this thing cost me about 25 euros because Arduino's like dirt cheap. Implementing the MIDI protocol on the Arduino has libraries and all sorts of stuff. It's really, really easy. I highly recommend trying it out if you want a bit of fun. I'll release the source code for this thing, but you might want to build your own source code from scratch. So, what's the conclusion of this thing? Clojure allowed us to experiment before going out and spending ages building a piece of custom hardware, which is really good. If I had known better, I might have tried some of the other approaches we looked at for generating random musical creations. But using Clojure allowed me to very quickly find out what it is I found interesting, and that's Euclidean rhythms. So it's fun, it's cheap to do this, especially if you can explore what's out there first. And there's many paths to follow from this. You can go back and look more into tone music, so actually playing real chords or making arpeggiators over the chords, programming arpeggiators. You can go back into rhythm theory, Euclidean rhythms is just one way of doing this stuff. Or you can look into synths. For example, you can look into overtone. Overtone gives you loads of it's a great tool for building your own synth from scratch, but you need to read up on your theory before you get to there. Yeah, and as I said, this is a guide. This is the 3 chords you need to go out and form your own punk band. And if you want to see this live demo and play around on your laptop, because you can do most of this stuff on your laptop for free, you can check out the code from the GitHub repo. And as I said, I'll put the Arduino version of this online as well when I figure out how to tidy up and tidy it. Cool. That's everything for me. Thanks.
Yeah, thank you, Thomas. That was super inspiring, and I feel very motivated to start using Clojure for music now. I think we have time maybe for one question, if somebody... Yes.
So this is part question, part feature request, I guess. Are you planning on some way to input MIDI into this, so that, for example, you could record a MIDI track and generate Clojure code from it representing the actual MIDI that you can then, I mean, maybe just a simple thing for starters, right? Just a sequence of notes that you can then play with within the software.
Yeah, I think it's a good question. Well, I mean, one of the things I've thought about doing is if you press multiple keys, right, you can see you get note on messages. You can read those into Clojure. It's easy. You can send them on the JVM in general. So you could like keep track of which notes to press down, and then iterate over those, and send that MIDI back to like the same device or a different device, and listen to it being played back. I think that's like probably the next step I'll play around with. So you press a chord, and then it builds like an arpeggiated piece of music over the chord, and you can randomize the arpeggiator, or you can you can do whatever you want. That could be like one project, yeah.
Great. Then, yeah, give another hand of applause to Thomas. And